Now till now we have seen that once the table is in second normal form, some of the redundancies have been eliminated, and these redundancies were mainly because of the partial dependencies. Now it doesn't mean that all the redundancies are eliminated, right? Even though a table is in second normal form, still there can be redundancies because of other types of dependencies. I'll show you an example. I'll just take an example and show you how a table in second normal form is not going to guarantee 100% redundancy elimination. Okay, so let us assume that we have a table with A, B and C, three attributes. Okay, now let's say the dependencies on this, the FDs which are applicable on this are like this: A determines B and B determines C. Now if you look at these dependencies and try to find out the candidate key, you will see that A is a candidate key because A plus is going to be A, B and C, right? And since the candidate key is containing only one attribute, there is no way that you are going to have any partial dependency, isn't it? Partial dependency arises only when a part of the candidate key is determining non-key attributes, right, or other attributes. Now if you see this, there is no part of the candidate key. The entire candidate key is a single attribute. Therefore there is no way that there will be dependencies, redundancies because of partial dependencies, or I can say that there is no partial dependencies in this, right? Therefore the table itself is in definitely second normal form, but still there can be redundancies in this which can be eliminated, right? So if you observe this, okay, I'll just take an example. See this. Now since A is the candidate key, it should be unique in the entire table, right? Let us say A is having values like this: 1, 2, 3, 4, 5, 6. Okay, and A is determining B, so B can be like this: B, 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 and maybe C, C, C. Okay, and along with that we have one more dependency which is saying B determines C, which means for a given value of B, you will be able to say the value of C uniquely, right? So what does it mean? If B is having some value here, same value, then C will also have the same value there. If two values of B are same, then two values of C will also be the same, right? So what I mean by this is, this will be like this. So if for one value of B, capital B, if its value is B and C value is X, then for all the values of small b, C value will be X only. Then only we can say that B is determining C. Given that that small capital B's value is this one, if they ask what is the value of C, then you can say that it is X always. That is the meaning of the determining, right? Okay, now B determines C means this is the meaning. Now similarly, if you say Y is here, then Y will be definitely here. Now if you observe this entire thing, let us say B is repeated 1000 times, capital B is repeated 1000 times, then C will also be repeated 1000 times. Since this is a small table, you might not feel that the redundancy is too much, but if you try to have a table which is having millions of entries, then for all the repeated values of B, C will also be repeated. So what could have been a better way of writing it? The better way would have been keeping A and B and C separately. So a better way to write it is, instead of having it here, remove it and create a small other table that will just contain B and C values. For the value of small b, value of C is X, and for the value small c of B, the value of C is Y. It is enough. Got it? Therefore if you ask for the value of capital B equal to small c, what is the value of capital C? Then you can say it is directly Y. So in order to say that, you need not maintain this entire row, right? Now why did this case arise is, if you observe it carefully, this A is a key attribute. Key attribute is determining B, which is non-key, and similarly B is a non-key attribute which is determining other non-key attribute. So that is called as transitive dependency. Transitive dependency means A is a key attribute, it is trying to determine a non-key attribute C, through a non-key attribute B, right, which means C is transitively dependent on A. So such kind of dependencies are called as transitive dependencies. So what is the way of understanding whether there is a transitive dependency or is there or not? If the left hand side of a functional dependency is non-key attribute, and if the right hand side is also a non-key attribute, which means if a non-key attribute is trying to determine a non-key attribute, then that is called as transitive dependency. Now because of such transitive dependencies, we are going to get such redundancies, and now these redundancies can be eliminated if we can split the table in such a way that you are going to take with this non-key attribute all the attributes that are determined by this into a separate table. Got it? Now what did we do? We are dividing the entire table A, B, C into two tables. One table is going to contain A, B, and other table is going to contain B, C, right? Now the intersection between these two is B, right? And if you observe this, B is a key for this. So if you see B plus is going to contain BC. Therefore, B is a candidate key for this table. So when the intersection is at least candidate key for one of them, you can say that it is lossless. So the decomposition is definitely lossless decomposition, right? And what about the dependency preserving? If you see this, A determines B and B determines C are applicable here, right? Therefore, dependencies are also preserved. So this table is saying that A determines B, so you have this dependency, you can apply this dependency on this table and you can apply this dependency on this table. Therefore dependencies are also preserved. So by splitting up the table based on the transitive dependency, we can see that the newly formed tables will all be in third normal form, which will reduce the redundancy, right? And now the third normal form, in the third normal form, it is lossless decomposition. When you are decomposing into third normal form, it is lossless decomposition and also dependency preserving. Now whatever I have explained till now are all under the assumption that the table is already in second normal form. So what is the meaning of it? First, we are seeing that the table is in first normal form. According to the definition of a relation, every plane table is going to be in first normal form, right? And then we are seeing that the table is in second normal form, which means there will be no partial dependencies, and after checking that, we are seeing that the table is in third normal form, which means whatever method I have applied here of finding the transitive dependencies and then decomposing the table according to transitive dependencies will give us the tables in third normal form only if the original table is in already second normal form. In case if the original table is not in second normal form, then also you can directly apply third normal form, but then we shall see other definition by which we can do that. Okay, before going ahead, okay, anyway we are always going to follow this. First we see that the table is in first normal form, and then second normal form, and then third normal form. Let's see some examples in which the table may not be in second normal form. First convert them into second normal form and then to third. Okay, let's see that.